So how exactly do we solve intelligence per watt? And honestly, why does our most cutting-edge AI fail miserably at basic reasoning tests when a human toddler can just intuitively figure them out? Think about it. We're pouring literally billions of dollars into massive compute clusters, yet our absolute best frontier models are fundamentally missing something that biological brains figured out millions of years ago. Welcome to The Explainer. Today, we're diving deep into some hardcore research from top Y Combinator AI folks to unpack what might be the single biggest bottleneck in modern AI and the exact architecture that could finally unlock true artificial general intelligence. Let's get into it.
Right off the bat, top researchers are pointing to one specific metric as the ultimate open problem in AI: intelligence per sample. You know, a human can sit down, look at a brand new board game, or try a completely novel physical task, and kind of get the hang of it after just a handful of tries. But our best AI, it needs tens of thousands, sometimes millions of data points just to grasp the absolute basics. The problem is, we've been measuring AI by its final high score, but true intelligence, that's about your rate of skill acquisition. It's about how much smarter you get with just one single additional piece of data.
Which brings us to the core concept we need to understand today: sample efficiency. It's exactly that, the rate of skill acquisition per sample. And here's the crazy part. Perfect sample efficiency? It actually requires 0 new samples. Seriously. Think about NASA trying to intercept an asteroid millions of miles away. They don't launch a million test rockets and just learn from trial and error crashes, right? No, they use Newton's second law of motion as a perfect, pre-programmed world model. The rocket just glides right to the exact intersection point because the physics are already perfectly mapped out and predictable.
All right, let's step up the complexity and look at games versus the real world.
To really grasp why AI struggles so hard in physical space, you just have to look at the raw mathematical breakdown. Think a game like Go. It has 361 board positions in an action space of roughly 361 possible moves. In the grand scheme of things, that's highly constrained. It's exactly why search algorithms, like the Monte Carlo tree search used by AlphaGo, absolutely dominated the game. But put an AI in a self-driving car. The state space instantly becomes infinite. You've got unpredictable weather, pedestrians crossing, endless pixel variations, and the action space blows up to over 365,000 combinations of steering and pedals. Move over to robotics, like a 16-degree of freedom robotic arm, you're suddenly looking at 10 to the 16th power combinations. AlphaGo's brilliant search method just completely falls apart against that kind of mind-bending scale.
So how on earth do we handle infinite complexity? Well, historically, we leaned on model-free reinforcement learning. You see a state, you map it to an action. Basically, it's behavior cloning. You see a stop sign, you hit the brakes. But here's the catch. In a totally chaotic, non-differentiable environment like driving in rush hour traffic, model-free learning just collapses. You literally cannot memorize enough actions for every possible scenario. You have to shift to model-based RL. You have to learn the transition function. This means the AI actually has to understand the underlying physics of the environment to dynamically predict, okay, if I do X right now, what is state Y going to look like a second from now?
Which brings us to biology's ultimate cheat code. Enter the world model.
Believe it or not, biology solved this exact problem about 10 million years ago during the Great Cortical Expansion. There is this famous cognitive science study from 1967 by a researcher named Richardson, and it illustrates this beautifully. They took one group of people and had them physically practice basketball layups for an hour. They saw 24% improvement. Standard stuff. But then they took another group, blindfolded them, and had them just imagine shooting layups. Those people improved by 23%, almost an identical jump in skill. This absolutely proves that humans are running a highly advanced internal world model. We don't have to physically stumble through every scenario. We can actually train our physical policies by running these hallucinated rollouts right inside our own brains. And this is exactly why AI researchers are currently obsessed with teaching machines how to literally dream.
So, how does an AI learn to dream? Let's look at simulating reality. The big goal right now is replicating this biological dreaming process entirely in silicon. And researchers are doing it through a 4-step synthetic training loop, which got incredibly popular with the Dreamer paper series. First up, you just feed the model massive amounts of passive video data. Think thousands of hours of YouTube. Step 2, the AI builds a latent world model that actually understands how objects transition from one frame to the next. Third, you apply post-action conditioning using just a tiny handful of real-world examples, just to map its actions to those transitions. And finally, you train the policy completely inside that neural simulation. By doing this exact loop, Dreamer v4 became the very first AI to successfully mine diamonds in Minecraft, using basically nothing but its own synthetic imagined data.
But, as you might guess, there's a massive technical roadblock here.
Trying to predict exact, high-definition future pixels frame by frame, it's computationally impossible. It's just too heavy. And that's where JPEG comes to the rescue. JEPA stands for Joint Embedding Predictive Architecture. Instead of stubbornly trying to predict raw pixels, it uses encoders to squash those massive state spaces down into a much smaller compressed latent space, and it runs its predictions in there. Now, to stop the model from just being lazy and outputting a bunch of zeros, which is a huge problem called model collapse, researchers use these variance-preserving tricks like SIG or VIC-REG. This guarantees that those compressed dimensions are still capturing the true, rich physical dynamics of the real world.
Okay, let's take this out of the software and into the real world, the robotics frontier.
Applying this latent space dreaming to physical robots actually solves one of the most maddening hardware hurdles in the industry, the cross-embodiment gap. Imagine you train an AI perfectly on a heavy Tesla Model X. If you just drop that exact same policy into a lighter Model 3, it's going to crash because the physical weight and dynamics are totally different. But by fusing open-source video diffusion models with world modeling, recent research achieved highly performant cross-embodiment robot policies using only 500 hours of teleoperation data. Just 500! By letting the AI dream and simulate in a latent space first, we effectively skipped the need for millions of real-world physical trials across all those different robot bodies.
Now hold your horses, because we are absolutely not at AGI just yet. Our experts highlighted a few brutal bottlenecks still standing in the way. First, physics-informed neural networks, or PINs, are still struggling. Standard gradient descent just can't hit true machine precision, like 1E16. Think about Steph Curry instantly adjusting his dribble when he hits a tiny dead spot on the hardwood. Current AI simply cannot model physics with that level of precision yet. Second is the sheer speed of test time planning. A human can adapt mid-swing. Models, they're still way too slow in the moment. And finally, hardware. Today's robots don't have a true tactile epidermis. Imagine if your hands were completely numb from the cold. You couldn't tie your shoelaces to save your life. Until our robots can actually feel friction, temperature, and shear force, physical AGI is going to stay bottlenecked.
But even with those bottlenecks, what's incredible is how perfectly this architecture is starting to mirror human biology. Look at this recent quote from a University of Washington paper. Each cortical area estimates both latent sensory states and actions, and the cortex as a whole predicts the consequences of those actions. When you apply the squint test to standard autoregressive LLMs, honestly, they don't look like true intelligence. They're just guessing the next word. But these latent world models, they align identically with how neuroscientists describe the actual human neocortex.
Let's rapidly lock in the core data from today before we wrap this up.
Here are the hard facts you absolutely need to remember. Traditional search algorithms burn an agonizing 24,000 model invocations per single step just to play a simple game of Go. When you compare that to a robot arm's action space of 10 to the 16th power, it mathematically proves that trying to brute force reality without synthetic dream data is totally doomed. But as we saw with the 23% boost from purely mental training and the fact that we can now train adaptable robots with a mere 500 hours of data, world models give us a definitive, mathematically sound way out.
So here is the big takeaway. If you remember literally nothing else from this explainer, remember this. True AGI requires maximizing intelligence per sample. And the only viable, scalable way we achieve that is by allowing models to simulate reality in a compressed latent space before they ever take an action in the physical world. The future belongs to predictive latent architectures, not just brute forcing next token prediction.
Which brings us to a final, slightly provocative question for you all. I want to hear your hardcore take on this debate in the comments. Do you think blindly scaling these autoregressive LLMs is a total dead end for real physical AGI? Are world models the only legitimate path forward, or is the industry missing something completely obvious? Leave a comment down below and let me know your stance. And hey, when you do, we'll send you our full, high-res technical mind map of this entire explainer to help you study up. Thanks so much for joining me. Keep learning, and I'll catch you in the next one.